This is Lab 2 for Physics 1. The purpose of this lab was to observe the motion of a falling object and to construct a computational model based on Newton's second law that includes first only the effect of gravity and then both the effect of gravity and the effect of drag. The result was that the graph with only gravity underpredicted my experiment data, while the model with drag was much closer to the experimental data. The reasons behind this will be further explained later. In order to get these results, I recorded a soccer ball being dropped. I made sure to drop the soccer ball right in front of a uniform wall of some kind so that it would be easier to track and so that there would be no spatial issues. I then put my video into Tracker where, just like in the previous lab, I specified the video frames, video timescale, and video length scale for the analysis. The diameter of the soccer ball, which was 0.22 meters, was used to calibrate the length scales in the video. I then chose the coordinate system so that the origin was at the center of the ball. I had to tilt the axis a slight bit to the left because the camera was at a slight angle. Identified the object's position in the video frames by continually plotting the middle of the ball in every single time frame. As the ball gained speed, it became a blur towards the last few frames, so I used the center of the blur as my best estimate. Doing this allowed the observed position versus time graph you see to appear here, with the data collected shown below. As you can see from the graph, its position is downward curving and going in the negative y direction, since the object was falling. The beginning of the graph is at the origin because we chose to start there due to the coordinate system, and it is at rest, which means its velocity is 0. After getting the data and plotting the graph, just as in the previous lab, I applied Newton's second law, which is this right here, to construct a computer model of the data. The final velocity is not equal to the initial velocity, which means the change in velocity is non-zero, which means that Fnet is also non-zero, so there has to be at least one force influencing the ball. Since we said earlier that the Earth exerts a force called the weight force on the object, we will start with a model that includes the weight force acting as the only force in the object and is therefore the net force. The formula is shown here. We will look at our computer model to see how this works, to predict observed motion. Now, before this computer model could be made, changes needed to be made to the code in VIDLE. The correct mass of the soccer ball, which was 0.45 kilograms, had to be put in. The initial position of the ball was set to 0, 0, 0, since we made the soccer ball start at the origin, and the initial velocity of the ball was set to 0, 0, 0, since the object was dropped from rest. We made t equal to 0, so it started when we started our observations. We set delta t to 0.001 seconds because my end time is 0.6, and we want the change in t to be very small compared to the end time. We had to specify g to describe the magnitude of the weight force, which is the g of W equals mgj. We also had to define the axis unit vector j hat, which specifies the direction of the weight force. We did that right below g. The time in the while loop was changed to our final frame, 0.6 seconds. Then the body of the while loop, which is where we predict the actual motion prediction using Newton's second law, was executed repeatedly until the time reached 0.6 seconds. In the loop, we needed to specify the non-zero net force of the surroundings on our falling object. Since we are assuming that the net force is only due to the Earth's gravitational pull, the weight, we need to translate W equals negative mgj into computer code. We did that by changing the line to what you see here, Fnet equals W. Because again, the weight force is the only force that is affecting the object. When you run the program, you see this here. The visualization is correct, and the plot seems like a close match. We then plotted our model data and our experiment data against each other so that we could see how well they predicted each other. As you can see from the graph, the model position underpredicted the experiment position. This is to be expected because there is one more force acting on the object that is not taken into account. When t is small, our model does a fairly good job of predicting the position. However, as t gets larger, it diverges more and more. This is because we did not force the lines into converging at the end by creating a fixed endpoint. All the rest of the endpoints after the first couple were true predictions. Now, we also wanted to make a model that showed not only weight but also drag as a force. The only change we had to make to the code was to add in the drag formula, which is this right here, and to find a suitable value for b. We saw that the final position in Tracker was 1.472, so we continually played around with values of b in order to find the best value that would get a final position as close to 1.472 as possible. That value was 0.172. We ran the program and got this right here. When we plotted our data, we got a model versus experiment graph that looks like this. As thought, when you include weight and drag on the object, the graph fits much better to our predicted model. It also helps that we force the drag line to end at a certain point to make it look better. But regardless, the drag model fit best because it takes into account drag along with gravity, when both are forces that are acting on a falling object. The middle diverged a little bit, which may be due to some issues plotting the center of mass and tracker. There may also have been some external factors such as the wind blowing. It is important to realize that the formula for calculating drag isn't exact, so that may also have contributed to the slight discrepancy. Now on to the what does it mean. Now as you can see from these graphs, the model without drag had no terminal velocity. You can see this because the graph has a constant slope, so it is continuing to accelerate at a constant rate. However, in the model with drag, there is a terminal velocity because the graph is flatlining. And terminal velocity is when your object continues to fall but stops accelerating, which is shown in the graph. Now, if an object is thrown downwards, the terminal velocity would be the same as in the previous graph. In order to show this, I changed the position and plotted the velocity versus time points to get this graph right here. You can see from it that the initial velocity doesn't affect the terminal velocity.